this is Adarsh Masukla. Here, I wanted to introduce Saraswati Rai, who is going to present today her work. She is doing PhD in Bits Plani under Sonokrai. So now I'm going to invite Saraswati. Please present your work. All the best.
Thank you, Adarsh. Good evening, everyone. Uh, my screen, I think it's visible.
Yes.
Yeah, you continue, please.
Okay, thank you. So, today I will discuss about my research work titled as Metal Oxide for Electrocatalytic Oxygen Evolutions Reaction or OER. So, before I moving into detail, I would like to explain why OER is significant. So now coming into the figure 1, as we can see, the growth of demand of primary energy is increasing day by day in the leading countries, and from the figure 2 we can see the worldwide consumptions of primary energy such as coal, oil and natural gas are 28%, 34% and 23% respectively. And according to BP Statistical Review, the year 2018 witnessed the fastest primary energy consumptions in the last decade, and it is also expected that in the following years the growing trends of the primary energy consumptions will increase more rapidly than the growth of the populations. And it is also predicted that coal will remain for next 150 years of use, and oil and natural gas will remain for next 50 years of use. Not only that, on the other hand, the uncontrolled combustions of the primary energy accumulated some greenhouse gases such as CO2 and other harmful gases like CO and NO2, as we can see from figure 3. And from figure 4 we can see clearly how the CO2 emissions has hiked in India and all over the world day by day. So this is the time we should think about some sustainable energy. There are some sustainable energy such as wind energy, hydroelectric power, solar energy and hydrogen economy. But among this, the former three has some disadvantages such as high cost, high installations area, and unavailability of sunlight all over the world and noise. But among this, hydrogen economy is the cleanest and sustainable substituent of the primary energy. So what is hydrogen economy? Basically, hydrogen economy is nothing other than the electrocatalytic water splitting. Basically, electrocatalytic water splitting is happening in two parts. The cathodic part is the hydrogen evolutions, and the anodic part is the oxygen evolutions. So, to form more, to generate more H2, the forward rate reactions of formations of O2 has to be also increased, but this anodic reactions OER, it is the main bottleneck for water splitting due to its sluggish 4 electron transfer reactions mechanism. As we can see here, the cathodic reactions HER is happening in two electron transfer system, and anodic reactions OER is happening in 4 electron transfer process. So that's why researchers are more focused on OER. So now coming into the mechanism of OER. Basically, OER is happening in basic medium, but it's not completely true. Completely true. Some of researcher has done these reactions in acidic medium also, like HClO4 medium. But the main disadvantage in acidic medium, as I have mentioned in my title, metal oxide for OER reaction. So in acidic medium, basically metal oxide are not stable, so that's why basically OER is happening in basic medium, and as we can see here in basic medium, OH metal M denotes here metal oxide. So in basic medium, OH finally converted to O2, and in acidic medium, H2O is converted to O2 by 4 electron transfer procedure. So as I told, OER is happening in basic medium. So I will show you more detail on reactions mechanism. Basically, the specific reactions mechanism is lattice oxygen mediated reactions mechanism, or LOM. Uh, for what is happening in LOM? Here, aim is, as I mentioned, aim denote metal. So here, metal form a bond with electrolyte OH, and then from here water is coming out, and the metal oxygen is for the formations of, we can see the formations of the vacancy. This is oxygen ion vacancy. So the name itself said lattice oxygen mediated reactions mechanism. So here in this oxygen vacancy, as we can see later, the OH is coming and sitting into, in the third step we can see OH is coming and sitting into the vacant side. So here oxygen vacancy is involved in that reactions mechanism, or we can say oxygen vacancy will enhance the forward reactions. And in absorbed evolutions mechanism, here basically no such kind of oxygen vacancy is needed. Only the electrolyte will come and sit into the metal side, but the basic difference is here, as we can see the metal oxidation state is changing here. So now coming into the my work, I have synthesized the normal spinel CO3O4, where cobalt 2 plus is sitting into the tetrahedral hole, and cobalt 3 plus is sitting in the octahedral hole, and oxygen is sitting in the lattice side. So basically, I have synthesized CO3O4 by three different methods, via solutions conversions method, and via solid state synthesis, and via calcinations of geolytical imidazole framework, that is a subgroup of MOF. So for SCA, solutions conversion synthesis, I have taken normal cobalt nitrate salt as a oxidizer, and glycine as a fuel, and for GIF67, basically I have synthesized first GIF67 from cobalt nitrate and imidazole moiety, and GIF67 is nothing other than the cobalt tetrahedral bridging in the imidazole moiety. So I have done TGA to check the thermal stability of cobalt nitrate and GIF67s, and as you can see, the cobalt nitrate stability is before around 300, and GIF67s is around 350. So from there I choose that temperature, and GIF67s I calcined under 450, and cobalt nitrate under 350. And finally I got this kind of normal spinel structure of CO3O4 in different synthesis process, and this is the same image of GIF67. So now coming to the characterizations. So I have done the XRD, and this figure 1 is the XRD pattern of 3 synthesized CO3O4. From here we can see this CLC denote the cobalt oxide synthesized from the cobalt nitrate, and SCS denote from the solutions conversion synthesis, and GIF is denote from GIF67. So What is the difference here? As we can see clearly for CLC and GIF, the XRD pattern is intense. Like we can see the for SCS, the peak is broadened. It's broadened. So from here we can say the crystallinity of CLC and GIF is more than the SCS, and I have calculated the crystalline size by using device error equations. That is, D is equal to 0.89 lambda V cos theta, where lambda is the wavelength of the X-ray, beta is the full width and half maximum, and theta is the corresponding angle. So from here I have observed for CO3O4 SCS, the crystalline size is 14.02 nanometer, where in case of GIF and CLC is 76 and 89. So it's quite higher. So from here also, I can conclude the crystallinity of CO3O4 SCS is less than the other two. So, to more insight into the crystalline structure, I have done Rydville refinement, and from here I have observed that cobalt 2 plus is sitting at the 8A, and cobalt 3 plus is sitting at 16D, and oxygen is sitting 32E Wyckoff sites, and the occupancy of oxygen, it is for SCS is 0.99, but for CLC and GIF it's almost near to unity. And from here I saw this is a cubic structure. As you can see, A equal to B equal to C, and this is the chi-square value, which is indicating the well fitting. So from XRD and Rydville refinement, I concluded that in CO3O4 SCS, there are some oxygen vacancy. As you can see here, oxygen occupancy is not 1. So some oxygen came out from the lattice side, and the crystallinity of CO3O4 SCS also it's less than the other two. So now coming to the FESEM, what I have observed here, for CLC, I saw that nano flex kind of structure, and for B it's quite interesting. When I have I have calcined GIF67 under 450 degree temperature for 6 hours, even though this cubic safe of GIF67, as you can see, it's still written there. But for CO3O4 SCS, the morphology is like, as I have done calcinations under high temperature for 10 hours, so it is kind of just a chunk, kind nano chunk. So there is no such kind of morphology. But for GIF67, this morphology is still written after calcinations also. So from here also, the crystal that particle size is half of for CO3O4 SCS half than the other two. So from here we can conclude that as the particle size of CO3O4 SCS is less than the other two, and it is in nano in structure, so the surface area also will be high for CO3O4 SCS. So to cross check this one, I have done into absorptions, desorptions, and what I have observed for CO3O4 SCS, the BET surface area and pore size also higher than the other two. So now coming to the TAME analysis. From TAME, I have calculated the average particle size of the three synthesized CO3O4, and here also I have observed the particle size of CO3O4 SCS is less than the other two. So from XRD and TAME and SAME, I can conclude that CO3O4 SCS is not purely crystalline. It's a nanostructure, and it has the higher surface area, pore size, and also less crystallinity size. So and even the oxygen occupancy also less than the other two. So now coming to the XPS survey. From here, we can I have observed the presence of the element from sorry, the figure 1. Extremely sorry. So from figure 1, we can see the presence of carbon, nitrogen and oxygen, ACS, and I have calculated the percentage. It is higher for
Saraswati, you take, I think you take water and then start. No, it's
it's
required
okay,
for
it's
that.
okay.
Oh,
So we can see from figure 1 the percentage of oxygen, nitrogen and carbon is higher in case of SCS. Why? Because as I have mentioned, I have synthesized SCS by solutions combustion synthesis, and I used glycine as a fuel. So that's why the percentage of nitrogen and carbon is higher in case of SCS. Now coming to the figure 2. Here I have done the cobalt 2p XPS, and after deconvolutions, what I observed, there is a peak. It's arrived around 780 electron volt, which is cobalt 2p 3 by 2 2 plus, and around 782 is the cobalt uh, 2 plus, and 780 is the cobalt 2 plus, and the peak around 794 is the cobalt 2 plus 2p 1 by 2, and 796 is cobalt 2p 3 plus 1 2p 1 by 2, and around 790 one satellite peaks arrived for cobalt 2p 3 by 2. So now from here I have calculated the cobalt 2 plus by 3 plus area. As I have mentioned in from Rydville refinement, I saw some oxygen came out from the lattice side. The oxygen occupancy is not exactly 1. Like here you can see oxygen vacancy is not exactly 1. So some oxygen came out from lattice. But CO3O4 is neutral. So if some negative charge come out from lattice, there should be some reduced of positive charge also to maintain the charge neutrality. So the cobalt 2 plus by 3 plus ratio will also increase if the oxygen vacancy is increasing. uh, 2 plus by 3 plus ratio, it is increasing means the intensity or the area of 2 plus is higher there. So when I calculated these things, I observed the cobalt 2 plus by 3 plus ratio in case of SCS is higher than the other two. That's clearly indicate the formations of oxygen vacancy more in SCS. It's compensate with some conversions of cobalt 3 plus to cobalt 2 plus. Now coming to the figure 3. This is the oxygen 1 is XPS, and here you can see 530 electron volt, one peak is there. This is for lattice oxygen, and at 531.51 one peak arrives. This is for oxygen vacancy. So from XPS also, uh, I have shown the formations of the oxygen vacancy, and I have calculated the oxygen amount of oxygen vacancy by OV by OT calculations, and there also I saw oxygen vacancy is higher for SCS. Now coming to the theoretical part, some DFT calculations we have done, and this is the from figure 1 we can see uh, the A, where there is no oxygen vacancy, only pristine CO3O4. O2 is coming here, but in figure B, where this dotted line is showing the oxygen vacancy, where H2 is coming more towards to the CO3O4 due to the vacancy. And when we calculated the Gibbs free energy versus reactions coordinated, we observe when there is no oxygen vacancy, this path needs higher energy, but with oxygen vacancy, it's need the lower energy. So from DFT calculations also we prove if there is some oxygen vacancy, the rate of reactions will increase, as I have shown in that reactions mechanism here, LOM. This is if the vacancy is creating here, then only the OH from electrolyte can go and sit into the vacancy, and then only the formations of O2, the forward rate reactions will enhance. So that's why oxygen vacancy in your synthesized metal oxide is the main descriptor to increase your oxygen evolutions reactions. What I what we have shown from Redville refinement and also from XPS. So and DFT calculations have shown that with oxygen vacancy and without oxygen vacancy, the difference of the reactions coordinated path. Now coming to the electrocatalytic activity. So the figure 1, I have done the cyclic voltammetry at the potential window 1 to 2.4 volt versus REG, and here you can see the red one, CO3O4 SCS, it is showing current density 330 milliampere per centimeter square, where the others two is showing only 30 and around 60. So it is quite higher than the other two. And around 1.4 volt, there is a intense peak, which is the formations of cobalt 4 plus from cobalt 3 plus. So when I have done these reactions in KOH medium in presence of electrolyte, as I have told in CO3O4, cobalt 2 plus and 3 plus is present there, but in presence of this reactions conditions, some cobalt 3 plus is converted to cobalt 4 plus. What I have shown in the insert, this around 1.4 volt. Now I have done LSV, and here I saw the overpotential for CO3O4 SCS is 1.23, is only 400 millivolt. That is quite less than the other. Actually, basically overpotential we are calculating, the standard is 1.23, from there we are calculating, and I have observed the current density and even overpotential is quite less, the overpotential is quite less and current density is quite higher than the other two. And now coming to the figure C, this is the Taffel's law. I have observe that Tafelslav value for ACS, the red one, is 84 millivolt per decade inverse. So that is quite less than the other two. So if the over Tafelslav value is lower, then we can say the forward rate of reactions is higher. So from electrocatalytic activity also, we observe that CO3O4 ACS showing higher current density, lower over potential, and the lower Tafelslav value. That's why, due to the presence of higher oxygen vacancy, it is showing the good catalytic activity. So now, coming to the impedance spectroscopy, the figure 1, this is the impedance spectroscopy. When this is CO3O4 CLC and CO3O4 GIF, I have observed only one single circle, but coming to the ACS, I have observed it two semicircle. And this two is the normal circuit, but the ACS is the Ujjwar kind of plot. So, and the RCT value, the resistance for ACS is 10 times lower than the other two. So from here, as the RCT value resistance is less for CO3 for ACS catalyst, that's why we can say it is highly conductive. That's why basically the current density what I have observed in CV or LSV, it is more higher than the other two because it is highly conductive. Now for the stability study, I have done chronoamperometry, and up to 2 hours my catalyst in that same reactions conditions, it is stable. And in figure 4, we can see this one is platinum C and one is ruthenium oxide. Basically these two are the benchmark catalyst what reported from last decade as a good catalyst for OER. So when I have compared my data with the benchmark catalyst, and it is far better than the benchmark catalyst. So from figure D, we can conclude that CO3O4 SCS is showing good OER activity than the benchmark catalyst. So now coming to the ECS, electrochemical active surface area, I have observed from BET the CO3O4 SCS is having higher surface area than the other two. So that now I have calculated the, when I have done the CV at that time, how much active area is showing. So when I have calculated this, and I observed that CO3O4 SCS ECSA also is higher than the other two. And now coming to the last figure, here I have done again oxygen one is XPS after after the oxygen reactions. So what is the difference here? Here you can see the four peak appears, but when I have done this oxygen one is XPS before OER, you can see clearly here three peaks present here, but after reactions, four peaks present here. This peak around 534, 533.5, it's a new peak. So basically, this is the metal oxyhydroxide peak. That's indicating your reactions is happening, because this metal oxyhydroxide is the formations of the RDS. I will show you the reactions mechanism once. Um, like here, as you can see here, metal oxyhydroxide, MOOH, is the RDS step, or this is the intermediate of your reaction. So when you are doing OER in that potential window and in that reactions conditions, definitely there will be the formations of metal oxyhydroxide species that we have observed up from oxygen minus XPS. The formations of new peak arrive at 534. And finally, we have compared some data with our CO304 SCS, and what we have observed that it is like, as we can see here, CO304 on graphene substrate or CO304 on some conductive support, it is showing around 300 millivolt or 400, but without any support. Only the beauty of the synthesis methods, it is it will enhance the wear activity, because I have synthesized CO304 by three different methods, and three are CO304, but it is showing so different OER activity. So this is like we have shown that how the synthesis procedure can change the catalytic activity. And as I have told that CO304 SCS is showing best catalytic activity over OER. Thank you.
Thank you, Saraswati. Guys, if anyone want to ask question, ask.
Can I ask something?
Yeah, bro.
So you are doing the OER reaction in alkaline medium, right? So in
Yes.
alkaline medium, I mean, if you disperse your metal oxide or metal in alkaline medium, it will form some hydroxide on the surface.
Yes, yes.
So then how, like after the reaction, you are saying that you are getting some cobalt oxyhydroxide. So that may be due to the deposition of hydroxide from alkaline also, right? So how can you neglect that thing?
No, if you're normally just dipping your catalyst in KOH and just doing XPS, you will not get such kind of peak. But if you're
You
putting
did that?
we have done this, but you will not get this kind of peak. But if you are doing in these things after OER in that such potential, and you are putting that voltage, the OER conditions, then only the new peaks will appear. Otherwise, it will not. It is not coming.
Okay. Because XPS is a surface phenomena, so if the deposition of hydroxide is happening, that then it will give the surface same characterization. That's why I'm asking. Okay.
Uh, Actually, if you are just normally dipping your catalyst into OH, then you will not get such kind of peak at around 534, that metal oxyhydroxide,
Okay.
but you will observe after OER only. I understood that it is a surface phenomena, so if OH is there, you can get that OH there.
Yeah. Because in the as synthesized sample, the second peak actually in the oxygen XPS is very broad, so you can fit that peak into two peaks also, right?
But then actually it's depend upon the fitting. So are you saying about the last XPS?
The fast XPS I'm talking about.
Or should I open that? Just a minute.
No, means in that synthesized sample you have fitted the oxygen XPS into three peaks.
Okay, before doing the OER, yes,
Yeah,
yes.
yeah, yeah. So there you did not dip the sample in the OH, right? I mean alkaline solution.
No, 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 no.
So that's what. If you dip the sample in the alkaline medium, for how long you are doing the reaction, and like this is like a blank reaction without any electrolysis. Just dip the sample in alkaline medium and take the sample out and dry it and submit for XPS. You will not see the COOH peak, right?
No, actually, because but I have done, when I have done just only 2 cycle for CV, then I have done the express, but there is no such kind of peak. But when I have done long cycle, means the reactions. When I did 2 cycle, this is the reaction just started, the onset, not reactions happened at the 10 milliampere hour. So when I have done for 1 hour chrono or 30 cycle, then only I am getting that peak. So when that reactions is happening, then only you can get the peak. If you're just normally dipping, like I dipped my catalyst into KOH, then I have run only 2 cycle of CV or 10 cycle of CV, I will not get that peak.
Okay, and what is the pH for this reaction?
This is I'm doing in 1 molar KOH, which is 14, pH is 14.
Okay, maybe for the 2 cycle it is not enough to deposit OH on the catalyst surface.
No, not even 2 cycle. If I'm doing 10 cycle also, 25 cycle also, we will not get it. So just like before doing LSV also, we have to do for 25 cycle of CV, because this will be the onset. Reactions will start after that. So if you're doing long cycle, then only we are getting, so that we can conclude as reaction started. So if you're dipping for 5 or 10 minutes, is it not sufficient to absorb OH into your catalyst?
Yes, that's what I'm asking.
That's the things I'm also saying. Ki, I have run 10 to 25 cycles, but will not get the peak. If you're doing for
Sure, like when you are doing the long cycle, so you do the same deposition of the catalyst in the alkaline medium and take the XPS. You will get the same spectra. You will not get the same spectra, right?
no, just if I'm not putting any reactions conditions, then I don't think so I'll get this kind, because I didn't get this kind of peak. After doing 1 hour chrono or 100 cycle, then only I will get this kind of peak.
And your like electrochemical surface area is more for SCS than other to synthesize samples, right?
Yes, yes.
So what is the like dominating? Which role is dominating here? Surface area or oxygen vacancy?
See, for a catalyst, like for OER, there are so many descriptors, not only oxygen vacancy. Even like oxygen vacancy is one descriptor, and as it is a catalyst, as we all know, for a catalyst, if you have the higher surface area, then catalyst will show the higher catalytic activity. So for a catalyst, higher surface area means catalytic activity will be higher. So for that reason, we can say the catalytic activity of SCS is higher. But for OER, there are some particular descriptor. One of them is the oxygen vacancy, because if oxygen vacancy is there, as I have shown in that reactions mechanism, OH is coming and sitting into the metal oxide side. So if some oxygen is coming out from lattice, then there will be some vacancy, so electrolyte can come easily, the hindrance things will be reduced, no? So that's why like for OER, oxygen vacancy is one descriptor, but as we will know ki for catalyst it is common, no? If you have your catalyst is higher surface area, then it will show good activity.
That I understand. The thing is, like if you have higher, lower surface area but higher oxygen vacancy, then you will get higher rate activity.
For OER, I think we can get it, because I think I haven't observed such kind of example, but as for OER, oxygen vacancy and EG occupancy, like this kind of things are the main descriptor. So probably I don't have idea about it.
Like you say TiO2, the normal TiO2 and the colored TiO2. You know colored TiO2, right? Black TiO2 thing. So the surface area in the black TiO2 will be bit less than the normal TiO2, but the oxygen vacancy will be more in black TiO2. So I can expect that the OER reaction will be more in black TiO2 than white TiO2.
Yeah, if oxygen vacancy difference, like it is not if oxygen vacancy is if point 0.4 and 0.4.8, I there has to be a such like particularly the difference has to be higher, like if the oxygen vacancy is more higher, I think it will dominate the surface area, because for OER oxygen vacancy is the main restricted, so I think so it will show the higher activity if your surface area also less.
So that means for that case, surface area doesn't matter much.
I think so, because I didn't observe such kind of things, so but what I understood for OER from some theoretical calculations or some experiment also, if oxygen vacancy is higher there, then it will enhance the OER activity,
That
where
I understand. So I'm just asking which one will dominate.
definitely I think that definitely oxygen vacancy,
Okay.
because yeah, this is the main descriptor, oxygen vacancy.
Okay, and in TAME images, you got the very less size of the cobalt Fe3O4, CO3O4 for SCS sample, like 2 to 3 nanometer, I think.
Yes, yes,
But when we saw in the same images, it is like chunk kind of thing, right?
yes, yes, due to the calcium issues.
So why in TAME images we are not seeing those kind of things?
Actually, I have not it done in 200. I just it was 120 bulletin, so like the clear image and all. When you were saying why this chunk kind of picture is not clear in tape.
Yes, yes.
Oh, actually, it was a biomolecule term, so did not get such kind of good structure. That's
That I don't think that is the problem. I think maybe the probably the dispersion of the sample in the solution was high, or maybe ultrasonicated for a longer time. But then also CO3O4 is the magnetic material, right? So it
yes,
will
yes,
it will always try to aggregate.
yes, yes.
So we should see the aggregation in TAME also. I don't know why you are not seeing, and the particle size of 2 to 3 nanometers means it is like surprising to get the metal oxide at 2 to 3 nanometer without using any ligands. So that is what means. Have you taken any lattice ranges for that?
No, 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 no.
Okay. Okay. And how did you calculate this weak of sight from Redfield refinement?
How did I calculate?
I mean, how did you get?
After doing Redfield refinement, you will get that wake up site from Vista.
Okay. Okay. I don't know this. Okay. Okay.
Like after Redfield refinement, there will be a generated zip file. So when you will open that one in Vista, it will be written there that wake up sites.
Okay. Okay. I didn't observe that. Okay. 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 That's all from my side.
Others?
Yeah, actually, I wanted to ask means the mechanism that you have shown. How
Yes.
did you have confirmed that means, and what kind of instrument you have uh, used to define these metal oxidation state means in your mechanism as you have shown? I just wanted to ask that.
Are you saying how did I get the reaction? Actually, this two reactions mechanism, it was actually it was reported
Saraswati, it
from.
is better if you show slide.
Yes,
Actually,
yes,
I
yes,
could
yes,
understand.
yes, 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 yes. This two, yeah, are you talking about this two?
Actually, I could not see that your
Just
slide. Your means it's taking time. That's what.
is it
Now
visible?
it's fine. Now it's fine. Okay, fine. Yeah, yeah, it's fine.
Others, can you
Yeah,
repeat your
yeah.
questions?
Actually, means the mechanism you have shown. Na,
Yes.
how could we say that this is the pathway of uh, OER reactions mechanism, which your catalyst is going in that particular
Okay.
path.
Actually, for my catalysis, two things is happening because
Okay.
um, as you can see here, for LOM, lattice oxygen mediated, means there will be the formations of oxygen vacancy,
Okay.
and for EM there will be the change of the metal oxidation state. As you can see, from step 1 to step 2, it is conversions of 3 plus to 4 plus.
Yes, yes, yes.
So now coming to my Rydville refinement. Rydville refinement, I have observed the oxygen occupancy, it's not unity, and even from XPS I have shown here the formations of the oxygen vacancy peak at 531 electron volt. So from here we can conclude some oxygen vacancy presence in CO3O4, synthesized CO3O4.
Okay.
And when you are coming to CV, this figure, as you can see here, at the potential window 1.4, there is a hump. So you can see in that inside red figure, black figure, and the
Yeah.
there is a hump that is actually around 1.442 volt per versus REG. That is basically reported for the oxidations of cobalt 3 plus to 4 plus. So here oxidation state of cobalt 3 plus and 4 plus also happening, and as I have concluded from XPS and Rydville, the presence of oxygen vacancy. So both is happening here, like formations of oxygen vacancy and metal 3 plus and 4 plus transitions also.
So means what I think that if we wanted to follow, means if we wanted to for our catalyst to follow a single mechanism, we should change the conditions or we should change the substrate only.
No, like no need to change any conditions. Sometimes your catalyst will have the higher oxygen vacancy, but it will not show the oxidation state changing of your materials. So you don't have to change any conditions.
Okay. And so what satellite peak tells us?
Satellite peaks means this is for like as I have told, cobalt 2p 3 by 2, no? So this satellite peak is for cobalt 2 by this satellite is for cobalt 2p 3 by 2.
Means what the information it gives? Actually, I don't know. I know. I don't know anything.
Actually, when the XPS means that it will X-ray beam will go and hit the core electron, right? So that when the excited electron will come out, then it will feel some Coulombic interaction.
Okay.
So because of that Coulombic interaction, this satellite peak will come. Okay. And this will happen if we have the d orbital in your sample.
Oh. Okay. Because of d orbital, you can
d or s or d or
okay. High orbital,
not the s.
Fine. This is just because of electronic repulsion, huh?
Yes.
Okay. Fine. Thank you.
I have one more thing. Like I mean, from the Rydville refinement, you got the occupancy is for SCS. It is just 0.993, right?
Yes.
So what is the error bar here? Like it can be 1 also, right? If the fitting is some...
It can be error, but fitting is like it's below even than 1, so like we can
yeah, 0.99 means we always used to say it is 1, right?
No, but for as you also know, for Rydville refinement 0.994, 0.995 is also different, because for Rydville refinement, even if the same parameter is 8.112 or 8.113, that is also different.
Yes, that I understand. So that's what I'm asking, like if you feed 2-3 times, you will get the same value?
Yes, even I have done for 1.7, then again it's reduced, below 4. So
Okay.
actually, yeah, normally if it is 0.99, then we can say 1. But actually for Rietveld definement, what we have observed, if it is 0.993 and 0.994, that is also different. From
Yes,
there
yes, that
also,
I understand. Like we can write 0.999 also.
yes, yes, yes.
That's what like how like what is the error? That's what I'm asking. And one more thing, did you try the ESR or EPR for this sample?
No, no, I didn't do ESR for this sample.
Because that is the direct proof for the oxygen vacancy, right?
Yes, but at that time, I haven't done
And,
this.
and magnetic properties you check
No, 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 no. For this, I didn't do.
because the crystalline nature is different, no? So the magnetic property also will be different.
Yes, but for this, I did not do.
I don't think that will help you in your catalysis thing. Just I'm asking.
Yeah, that actually, what are you asking? No? That magnetic study that will help to. I mean, but I have understood that will help to understand your material structure, structural study. So here I haven't done this.
No, because in CO3 or 4 the particle size is less, right?
Yes, yes,
So the magnetic property also will be less, and when particle size is less, then like the disordered structure, surface structure will be there. So the oxygen vacancy formation also will be more.
okay. No, I haven't done this.
Now this is not related with the magnetic property. I'm just saying
So
that
oxygen.
yeah, the to create more oxygen vacancy in smaller size sample.
Yeah, the another kind of proof that oxygen vacancy is. I understood, but no, I haven't did this.
Okay, okay. Okay. Thank you.
Thank you.
Saraswati,
Yes.
in that GIF method, you mentioned about that emergol or indole, something you used for some chemical. Now, what is the purpose of that one?
As I have told that G67 is the cobalt tetrahedrally bridging with the imidazole moiety. So that is a ligand.
Okay, okay. So in this, you done with three methods, na? SES and CLC and GIF.
Yes.
So in this case, what is the more priority one? SES only, na?
Yes.
Okay, so here I think Dinu asked this at one peak, na? Last one, I think XPS data.
Yes, yes. Should I open the result?
Yes, yes,
I'll open. Is it visible?
Yes, yes.
Are you talking about the last one? This one?
Yes.
Uh,
Here that water also because of that vacancy of the oxygen only. That OH2.
no, this is like absorb water molecule. This is not for oxygen vacancy. Oxygen vacancy peak will come around 531 electron volt or around 531 to 532. But this peak is for absorbed water molecule in your CO3, not for oxygen vacancy.
Just to go back once to one or two slides, I think you show the AB one thing, not this one, not this one. Here, just next one.
Are you talking about
Not this one.
thing?
Next slide.
This one?
Here you mentioned about the in A figure, it water molecule is little bit away from the figure, but in that B figure, that water molecule comes together to the oxygen vacancy. So what is the thing that one?
Okay, we have done some DFT calculations. So there we have observed that if this is the first A is the for normal pristine CO3O4, there are no vacancy, but with vacancy the oxygen is coming more towards to your catalyst. This is H2O. Basically, I have told you OER is happening in void medium or in acidic medium also. So basically H2O is converting to O2. That's why we have taken H2O is coming towards to your catalyst. So when in figure A, when oxygen vacancy is not there, that attractions is very less, but when the oxygen vacancy is there, as I have mentioned, if some oxygen is coming out from your lattice, that means first oxygen form the bond with cobalt. If one bond is breaking, that means the hindrance, the your synthesized compound is less hindrance. So OH can or H2O can come easily towards to your catalyst.
Okay, okay.
That we have shown from DFT calculations.
Okay then. From my side also done. Thank you so much, Saraswati.
Thank you.
Thank you guys.
Thank you and congratulations, Saraswati.
Thank you.
Thank you, bro.
Thank